Doing all right this morning? Thumbs up. We don't start until everyone's ready. That's how lectures work, right? Morning. Still got another minute. So for those of you here, any folks started on the homework? Now, some of you have, so if some of you had office hours. Not, highly recommend you getting started. Okay? Especially if it's been a while since you simulated a dynamical system, or it's the first time you simulated a dynamical system. And there should be plenty of hints online on the Canvas page. But if not, we have office hours 4 days a week for this class, between the TAs and myself. It'll be fun though. We're simulating tumors and pendulums. All the world is made of, apparently. Tumors and pendulums. That's not literally true. All right. Sounds good. Let me start recording here. All right, good morning. Good morning, folks. Let's start that, Nick, at about 15 minutes in or so. Okay. Yeah. So welcome to another class. Hope folks have taken at least a look at the homework. I really recommend getting started early because, and as you'll find in coding-based assignments, coding assignments tend to throw more wrenches in the works than you might expect, than your typical course might have until this point. Keep in mind, we have 4 office hours a week, and we have the homework FAQ page. All right, nice link right on the front page of Canvas, homework FAQ. You click on it, and it has a lot of questions that have been asked over the last couple times I taught this assignment, okay? And I'm adding to it. We just had some questions yesterday at the office hours I thought would be useful to add the FAQ as well, so I'll add those as well. So anyway, good luck simulating the, chemotherapy. We're simulating chemotherapy and a pendulum on a cart. And the latter uses an animation. So if you have it, and thankfully we covered everything you technically need to do the assignment as of Thursday, where we did a animation of a what, friends? What did we animate? Pendulum. Yes, you all sound extremely confident. Yes, we animated that pendulum. So you have all the tools you need to do the assignment, okay? And believe me, having a video at the end of your homework, pretty fun. I don't know. I guess I'm giving the assignment. It's easy for me to say. But regardless, we have been, to date, simulating these pendulums on a cart. These pendulums, to date, these dynamical systems, and what we're going to, and so as a result, we're doing a lot of control stuff, dynamical systems and control. But before control in this course title is optimal, right? We haven't done a lot of optimization yet. That's by design. We wanted to show you a little bit of control first, a little bit of dynamics. Then we're going to show you how optimization plays into it. So we're almost to the point where we're getting back to optimization. But the last topic I want to cover before we get there, okay, is going to be linearization. So let's talk a bit about linearization. See how fast we get through that. So linearizing dynamical systems. Okay. So we have been simulating a number of these systems, okay? In last class we were simulating the pendulum. Swings like this. Okay? And the lecture before we were talking about linear systems. Okay? So we had pendulum dynamics as an example. And I swear we'll do things other than pendulums soon. But controls people love it. It's a nice, simple example of a particular kind of system. Again, you have your pin joint, you have your stick attached to a mass that is a point mass, and it's all under gravity. And then you define your angle over time relative to vertical. And I'm pretty sure in my dying breaths, when I depart this mortal coil, those words will be theta double dot is equal to minus g over L sine of theta of t. Such is my life. Okay? So now, are these dynamics, is this system linear? DJ, where's the nearest weapon? Everything's a weapon, if you try hard enough, I guess. Okay. If it continues, would you mind being polite? Thank you. Thank you. All right. Cool. All right. So we have here these dynamics. Are those dynamics linear, friends? No, you see head shaking. Why not? We have this sine of theta of t. But who here did the dynamics of a pendulum, the equations of motion of a pendulum in a physics class? Yes, yes. Yes, so some folks did. Did it have the sine of t by the time you were done with it? Does anyone remember that from class? I see you're shaking your head as well. All right, DJ, do your magic. Sorry, I don't know how much people on the stream can hear. That is it just me hearing the heartbeat from under the floorboards, or okay? No, it did not have a sine of t. Why? What happened? Correct. So what he said was that we assumed that sine theta of t for a small enough angle, close enough to the vertical, sine of theta. So sine of theta of t is approximately equal to theta of t when theta of t is small, right? And in which case, we would say that theta double dot of t is approximately equal to minus g over L times theta of t. So while this is, my friends, nonlinear, this, however, is linear. And you can see it in the fact that all of our dynamics are dependent upon some constant times our time varying quantities here, okay? That's a linear system. We can actually solve that linear system by hand. Question. But that only covers if theta is small. That's correct. So it is what we call an approximation, meaning it's wrong, okay? But is it usefully wrong? Okay, and that is that is the classic the classic conundrum of what we call modeling. All right, which is you would ask yourself, is the model that you're coming up with useful? So that's equation right here. Okay, that's not literally the physics of the world. It's much more complicated than that. We assume that this pendulum is a rigid pendulum connected by a rigid rod. But, you know, nothing's truly rigid in real life. If it was, it would violate physics. This is my thought experiment. If you had a infinitely rigid rod, and you made it long enough so it goes to Mars, right? I could wiggle it on one end, and on the other end, it would instantly wiggle on the other end, and that would violate relativity. I'm sure you've all thought of this many times. Okay, but my point is, like, it is an approximation that rod is rigid. Is it a useful approximation? Yeah, does a pretty good job. There's an adage that has been used in many different ways in many different fields, which is that all models, meaning this math model of the pendulum, all models are wrong, but some are useful. Okay, so as the student brought up, that yes, it's wrong that this only works well. This approximation is only good when theta at t is small. Okay, but is it good enough for what you want to do? Sometimes yes, sometimes no. So But where does that come from? So you might have been wowed and amazed by your physics professor when they brought up the idea of this small angle approximation. Like, oh, how clever. Can I always come up with those clever ideas? But what if I'm not so? What if I don't know that factoid that the sine of theta of t equals or is close to theta of t when the angle is small? Well, that is just one example of what we call a linearization. Okay, so here we have linearized the dynamics about theta of t equals 0, meaning when it's close to 0. That's another way of saying that, okay? And if you were to plot on this axis theta of t, and on this axis sine of theta of t, we all know what a sine wave looks like. Looks like this. Woo. Sound effects optional, right? Okay. But at this point where theta equals 0, if you were to draw a tangent line at this line, that tangent line will be equal to, let's see, so that basically is a 1-to-1, that's a, sorry, that's just equal to theta of t, meaning it's just a diagonal line, okay? So if we said that, say y is equal to theta of t, you say y, I can't see that very well, I apologize. All right, so we have locally linearized that rule, okay? Now, theoretically, my friends, you could choose to linearize about some other point. What about theta equals that? Okay, well, you could draw a tangent line right there. So it doesn't matter that you know this one factoid that this sine of theta is approximately equal to theta when theta is small. There are ways to apply linearizations to all kinds of functions and other points that we care about. So just to put a fine point on it, your dynamics are if you linearize about a particular angle where theta of t is small, the further you get away from the theta of t, the worse you get. Okay? The worse the approximation gets. So if you have a pendulum that's swinging around and around and around and around, it's going to be a horrible, horrible approximation. Okay? We'll do an example of this on our Tuesday coding lecture, where we will do linearization in MATLAB to compare. Okay? First, I need to show you how to do linearization. Any questions about this so far? Because if you know how to linearize something, yes, question. No, actually mean theta of t in this case. Okay. I'm trying to point out that, no, it's good point. Normally, good eye. Because if it were just t, okay, you could do t and sine of t, it would look like a sine wave, right? This is just trying to compare what happens with theta, what happens with sine of theta. They're approximately equal, right? Because we're comparing them up here. All right. So, and why do we care about linearization? Well, we do lots of cool stuff with control if our dynamics are linear. Okay? We can do lots of cool things. Remember we had this, so y linearize is a powerful form for analyzing and controlling the dynamics of a system. Recall that once your dynamics are linear or linear time invariant or LTI, we could put them in this form of x dot of t is equal to a x of t plus b u of t. Okay. Why linearize? And with that form, we were able to come up with controllers. For our control input, we had what we call a regulator or a controller. They're very similar, it's slightly different. We have a controller or a regulator. My handwriting is or a regulator, where you say u of t is equal to some minus k times x of t. What did this k stand for? What does it mean? Had a few k's in the past lectures. Yes? Gain. These are our gains. Remember we were choosing proportional derivative gains in our last lecture? Who chose them? We did, right? If our system is linear, though, there are lots of techniques, tons of them, that you can automatically choose the gains k, okay? Depending upon what you actually want the system to do. So it's very nice. So, and in addition, we were able to say, hey, this A matrix, we could take what we called the eigenvalues of that A matrix, and it'll tell us if the system is stable and how stable it is, right? So very handy to do, okay? So how to linearize? Okay? One is you have to choose an operating point. For all states x of t and inputs u of t. Such that x dot of t is equal to 0. Okay? This is what we call this a fixed point. Some people might call it a stationary point, call it a fixed point. Looking good, Nick? Good in the frames as well. This is what it comes down to, friends. So just like with the pendulum, we chose, hey, what about a small angle? Why do we care about that small angle? Do you remember why your physics professor chose that angle to linearize about? Any thoughts? It simplifies the model, that's true, but why that particular angle? Well, it's probably because we spend, when the pendulum's swinging, it's going to spend a lot of time near that angle, right? That's one reason. Spends a lot of time near that angle, right? In addition, that angle where the pendulum is straight down, if you're not applying any force to it, it has no initial speed, that will the pendulum will stay there, right? It'll just stay there. Okay. But that's not the only spot on a pendulum where that's the case, right? Where else can you position the pendulum where if you just stick it right there, don't breathe on it, and it stays there? Yeah. You're raising your hand, or you're giving me the answer. Both. Both, yeah, straight up, straight up, straight up. Okay? Both of these on the pendulum are example of fixed points, okay? Because at this state where my pendulum is straight down, which on my diagram would be the angle of 0. And how many states do we have for this system? We've done it enough times. Hopefully you know the answer. 2. 2 states. So you have to say what the other state is in the fixed point, which is our other state is our speed. So we'll say our speed is 0. Okay? And we're not touching it. Okay? This is the inverted fixed point of a pendulum. Okay? So I'll show you an example. So we'll just write this out as an example. For our example, for our pendulum, we have 2 fixed points. We know this intuitively from the fact that we have seen a pendulum, or if you haven't, I've yelled at you about it enough times you can imagine it in your heads. Okay? All right? Down and up. 2 fixed points. And what you want to do is you need to pick a state where the derivatives are 0. We call that x star. And our control inputs, which will be u star. Okay? This is our fixed point. We intuitively know down is a fixed point, assuming that it's not being pushed. Let's recall our pendulum dynamics in state space form. In state space form. Okay? Where we have our states, x dot. That's the derivative of both of our states, and the way we derived it in the past, that our first state is our angle theta. And so the derivative of theta is theta dot. And the derivative of your second state, theta dot, is theta double dot, all with respect to time, of course. And written in terms of our states, in state space form here, theta dot is a state. Look at that. Makes that line easy. And the dynamics of the pendulum were minus g over L for the acceleration times sine of theta of t. I also added a torque on here. That's important for a control input. Plus our control input tau of t over ml squared. Okay. We did that in our last lecture. This is just saying minus g over L sine theta for a pendulum, plus a torque that's attached, and that ml squared is the moment of inertia. You can derive it in all sorts of ways. Okay, now we've got, so now if we assume that x star, which is our 2 states at our fixed point, call it theta star and theta dot star, where this one is 0, this one is 0, and our control input u star, that's our torque star. We say that that's equal to 0. Then that means that x dot star, x dot, okay, and these are of t, I apologize, right there. This is x dot of t. If you then plug in your theta dots, your theta, your tau, it's going to be 0, and then minus g over L sine of 0 radians plus our tau at our fixed point is 0 over ml squared. Mathematicians will tell you that both of those values are 0, and therefore is a fixed point. At that fixed point, your first state angle over time is not changing. Your second state velocity over time is not changing. Okay? And we also know there's another fixed point, right? Where the pendulum's at the top. In radians, that is what, friends? Oh, it's early. What's 180 degrees in radians? Pi. Okay? Whoop, at pi. And we can do this without writing out everything. If we go back to this same formula, this is still the same, right? That's 0 for speed, 0 for torque. We're keeping that the same. And sine of pi is again 0. Okay. Technically speaking, you could say 2 pi and then 3 pi and minus pi. But functionally, I'm saying there's 2 fixed points. Technically, there'd be infinite, okay? But they're basically the same. Okay? So it shows in the math that those things are fixed points. So even for systems that you do not have intuition for, all you need to do is find all the states and inputs that make your fixed point 0. That's how you find a fixed point. Okay? All right. Any questions about that? Now, it also does, and also here, I also lied. I'm sorry, didn't mean to lie. You can come up with can you make this a fixed point? Well, not without a torque. But what if this was sitting still at this angle? We could choose that angle right there, but then we choose a torque that makes these two terms equal and opposite, right? Then that's now a fixed point too. The only difference is that our tau of t is not 0. Okay? Neat, right? So there are all kinds of fixed points, but things that are not fixed points technically would be if there's any speed to the pendulum. Because I can't zero that out in any way, shape, or form in the math right there. So you just have to hope it's close enough to what you want. Or you find some other you use some other technique that doesn't require it being a fixed point. Okay? All right. But to linearize our system, to turn it into this x dot is equal to ax plus bu, we're going to linearize about a fixed point. So that's step 1. Okay, I won't gild the lily anymore on that. Okay, so 2, take the derivative of your dynamics with respect to states and inputs. Okay? We're used to taking derivatives with respect to time, right? Now we're taking derivatives with respect to states and inputs. This is going to introduce a cool new term that might be new for some of you. Okay? We know what a derivative is, right? A derivative is typically when you're taking the derivative of one quantity with respect to another. Angle over time. You know, my hunger over lack of eating. Okay? Things like that, right? What if you have multiple quantities? In a vector, let's say. How do you take the derivatives with respect, because states are in a vector, right? You have multiple states. You can have multiple inputs. It's totally chill, the things that exist. So we have to introduce, there's a term for when you are taking derivatives with respect to vectors, okay? And the general term for it is a Jacobian. Okay. Sounds fancy, but really all it is just more derivatives. You like derivatives? Here's multiple derivatives. Okay. So for instance, here's an example of a Jacobian. Okay. Let's create a vector we'll call A. And it contains A1 and A2. No time involved. This is just a vector. Okay? And another vector, b, contains b1 and b2. Okay? The partial derivative of the a vector with respect to the b vector is actually a matrix, and that matrix is the Jacobian. Okay? What does it look like? Just an example. So it'll be a 2 by 2 matrix, partial A1, partial B1, partial A1, partial B2, partial A2, partial B1, and partial A2, partial B2. See that? That's your example of a Jacobian. Looking good? Okay, Nick? You can see I have every combination of A1 and A2 there, right? You'll notice that in the first row, I have all the A1s. In the second row, I have all the A2s. Okay? So if I were to write this here, I would say, the top vector index is the same. Gosh, I look like I'm a 3-year-old writing this, excuse me. Okay. Index is the same. Okay. And then for every column, you'll notice the bottoms are the same. Here's B1, B1. Here's B2, B2. Okay? The bottom vector index is the same. Okay? And this works for any arbitrary number of elements in those vectors. And they don't have to be the same size. So, if instead of having 2 elements in this top vector A, which gave me 2 rows, right? If I had 3, I now have 3 rows. Even if I still only have 2 of these B's, it would be 3 rows and 2 columns. If I add another element of B, or I take one away from B, let's say I scratch out this B2, what changes about my Jacobian? Anybody? Yes. It would cross out this column. So it would be a 2 by 1. Yeah. So it's easy to get that. So it's rows then columns, so it would be a 2 by 1. So because the bottom vector index is the same, it means that the number of columns that you have is equal to the number of indices you have in that vector. Okay? That's like the speed run Jacobian lesson. Okay? Let's just do a quick example, okay? Let's just say we have an example. We're going to create a vector we'll call y. Okay. And y has 2 elements, x1 squared plus x3 and x2 squared minus 3x3. That's a vector. And you have your vector x, which contains x1, x2, and x3. What is partial y, partial x? it's the derivative of a vector with respect to a vector. So we'll call it a Jacobian. Let's follow our format. Okay? So we could think of this element here, we could think of that as y1. We could think of this as y2. So we know it's going to be equal to the number of rows is going to be the number in the top here, y. We're going to have 2 rows. We'll write that out. It's going to have 2 rows. And it's going to have how many columns, friends? 3 columns. 3 columns. So we would call it a 2 by 3. And the level of linear algebra we're working with right now is just knowing what rows and columns are. Okay. Good. So if we fill it out via the formula we have up here, where the top vector indexes are the same in a row, that means that it's going to be partial y1, partial x1, partial y1, keeping the y's constant, right? Partial x2, and you count it up. And then partial y1, partial x3. I make a little bit more room. I have a rule that I constantly break, which I shouldn't close off the brackets until I've written everything inside. Otherwise, I box myself in. Partial y1, partial x3. Right? What's the next row? Anybody? Partial y2, partial x1 through 3. That's perfectly concise. Partial x1, 2, and partial y2, partial x3. Let me make a little more space on the board so you can all see a little better. 2 by 3. And there we go. Right? Question? So you're asking if we have an expression here instead of a variable. That's not something we will ever do. In which case you would have to take it. So let's say this was like x1 plus x2. That's like some other quantity. You'd have to determine, hey, how do you take the derivative of some? It's more of a partial derivatives question than it is a question about Jacobians. Okay. So, but in this class, I would not worry about such a thing. Okay. We will always be taking derivatives with respect to states, which will be a variable, or inputs, which will be a variable. Okay. Can you do that? I mean, I'll be honest, off the top of the head, I haven't thought about that in a while. Okay. All right. Well, you get this formula, though, right? Fill that out. So all the cool expressions, they're going to be in the top in all of our applications. So look, we wrote this out, but but y1, we didn't actually take these little mini derivatives, did we? So let's do that real quick, okay? So partial y1, which is this, partial x1, remember partials are the easy derivatives, right? Where everything that isn't that variable is a constant, which means that the top here, x3 is a constant with respect to x1. So that derivative goes to 0. You're only taking the derivative of x1 squared with respect to x1, which I'm sure you all know is 2x1. All right? Next term, partial y1, partial x2. I don't see any x2s there, do you? 0. Finally, partial y1, partial x3. I do see an x3. Derivative of x3 with respect to x3 is 1. Partial y2. So we got to go up here, and then partial x1. Well, I don't see any x1s. 0, my friends. Partial y2, partial x2. Partial y2, I see an x2. This is a constant, so that goes to 0. So it's going to be 2 times x2. And finally, partial y2, partial x3, y2, x3. Oh, there's an x3 with a coefficient of 3. That's Jacobian, right? Nobody exploded. Okay, yes? It should be a -3. I was testing you, Christian. You passed. Congratulations. Applause for Christian. Sorry. I got excited by the Jacobian. So, who's scared of Jacobians now? You can be honest. But if you can take a partial derivative, which is the easy derivative, you can take a Jacobian. All right? Okay? So, that's just an example of a Jacobian. But here, in general, our state space form is x dot, where that is, again, our state space, our state vector derivative. Again, the dot is the derivative, of course. Okay, of t is some function of x of t and u of t, right? That's why we write our state space form, and I forgot my little bars. Boop, 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 boop. Apologies if I forgot the bars on the vectors. At some point, I'm going to give a lecture, and I'm going to say, hey, guess what? Bars are gone. Not the fun bar, but the bars over our vectors, okay? All right. Okay. In general, our state space form is that. So for this step, we're taking the derivative of our dynamics, which is that, with respect to our x of t and u of t. All right? So let me write that out. So it's going to be the partial derivative of that function f. Again, we wrote that out for our pendulum. It's not that complicated necessarily. Okay? X of t, u of t, bar, partial x of t. That's a Jacobian. And you'll notice that it might still have variables in it, right? In this example, we still have variables in there. Just note that. So this is our derivative. This is with respect to states. And then our derivative with respect to inputs. Sorry, and so it's to be partial u of t. That's with respect to inputs. Okay? You want to take that derivative. Okay? So we've done two things. We've created a fixed point, and then we've taken these Jacobians. Now we're going to put them together in step 3. Okay? Step 3. You're going to put in state space form for an LTI system, my friends. Remember, that's x dot is equal to ax plus bu. And guess what, my friends? That A matrix is this. It's that Jacobian. That B matrix, it's that. One little catch. You have to plug in your operating point, your fixed point. Okay? Remember, you still have variables in here potentially, right? And if you do, if you still have states in there, plug in the fixed point for that state. If you still have an input in there, plug in the fixed point for that input. So the way we would write that is we would say that A is equal to the partial derivative of x of t comma u of t. Those are your dynamics. Partial x of t, that's your state, and you evaluate it at x is equal to x star. And you just plug in x star. That's just the formula for how you get the A matrix. I think when I did that before, I was just like vibing out. And I was like, I can grab that coefficient here. I can grab that coefficient here. I can write it in this cool way. This is the mathematical way to do it. This is the mathematical way to find those coefficients like I did a week ago. You just follow the formula of the Jacobian. Now, the B matrix, same deal, except, oh, and also you have to plug in U bar is equal to U star. So if you, of course, have a control input, you have to know what that control input fixed point is as well. X bar of t, U bar of t. This is the B matrix, so you take the derivative with respect to U bar. And I forgot the of t right there, friends. Excuse me. And you evaluate it at your fixed point again. And that's it. That's the general formula for how you linearize a system. If you have a fixed point and you have your dynamics in state space, this is how you linearize it. You don't have to be as clever as your physics professor to know the small angle approximation. Guess what? This would find it for you. Let's prove it with our example. Before I go, any other questions? It's very exciting. Take a nonlinear system and make it linear, and you do all the cool linear things. That's pretty nice. Almost too good to be true. But what's the catch? Cricket knows the answer. Is if you get far away from that fixed point, it's not going to work anymore. No longer a good approximation. So your analysis that you did with this A matrix and B matrix, it might be no good. It might be completely wrong. The controller that you used, that you came up with, those gains, those Ks that you use A and B to come up with, could be terrible. Right? So it depends on how good your linearization is. All right. So let's do an example with our friend the pendulum, where we had our state x star is equal to, so it's going to be theta star, theta dot star. We'll have the down position, and that's the angle is equal to 0. That's going to be 0 radians and 0 radians per second. And our U star, which is our tau star, our input torque, is going to be just 0 Newton meters. Okay? And we're going to prove that the stuff that you got in that physics class years ago, or however long ago you took physics, will just pop out of this. Okay? So this is our fixed point. We're going to linearize. This is our fixed point. Okay, so that's step one. We found a fixed point. We went in knowing what it was. Number two, we're going to do partial f, partial x. Now that's that same thing. That's to be clear, that's this. I'm just getting rid of all the stuff. Okay? Partial f, partial x. Okay? Now you'll have to recall that our f, which contained x of t and u of t, we wrote it above. It's got theta dot of t and minus g over L sine of theta of t plus tau over ml squared. And that's a tau of t. Okay. We need to take the derivative of this with respect to x, calling that x bar is theta of t and theta dot of t. Okay? So partial f of partial x is going to be a matrix. The partial f partial x, it's always going to be square. Means it's going to have the same number of rows and columns because the number of state derivatives, x dot, is the same number. You have the same number of those as you have states, right? Therefore, you're going to have this many rows, this many columns, and it's always going to be the same number. And we have two states, so it's going to be a 2 by 2. Okay. So if you all covered state space and controls 1, does anyone remember state space from controls 1 or just the words state and space together? No one remembers it. Okay. All right. This is where that comes from. So in the first row, given the fact that this is our first row of f is there, right? So we'll call it we'll say partial f1, where this is f1, and this we'll call f2. So it's partial f1, partial x1, partial f1, partial x2, because again, we're keeping on the same row, we're keeping the top the same. These change. Second row, we got partial f2, partial x1, partial f2, partial x2. Again, we're keeping the top the same on the same row. Look, the columns are the same in the bottom. Make sense? So now we just got to fill this out. So partial f1, this is f1. Partial x1, this is x1, right? So what is the partial derivative of theta dot with respect to theta? 0. The fact that they both happen to have theta as letters is irrelevant here, okay? Partial derivative of theta dot with respect to theta is 0. Treat it as a constant. Okay. Now partial derivative of theta dot with respect to our second state, theta dot. What's that? 1. Okay. Now we have f2. This is f2. Partial derivative of f2 with respect to our first state, theta. Well, I see a sine of theta, right? Minus g over L sine theta. This is going to be minus g over L cosine theta of t, right? And finally, we have partial f2, partial second state, theta dot. I see no theta dots. It's 0. Make this a little wider. That's a 1. That's a 0. So now we have partial f, partial x. Now we need partial f, partial u. Now, unlike partial x, there's no guarantee that the number of inputs is going to be the same number as the number of states you have, right? We have one input, 2 states. You could throw on 50 inputs for some reason, but still have 2 states. So that means that our matrix here isn't necessarily going to be a square matrix. It'll often be rectangular. So it's going to include partial f1, partial u1, our first control input, and then partial F2 partial U1. Because you have two states, one input. We can write this out pretty simply. I have to scroll back and forth a little bit, I apologize. Okay. Partial F1, partial U1, where U1 is our torque. I don't see any torques in F1, so that's 0. Now, partial F2, partial U1, U1 is our torque. There's our torque right there. So the coefficient is 1 over ml squared. And this, of course, is going to be treated as a constant. There's no torque there. So 1 over ml squared. Boom. That's your partial F, partial U. Cool? Glad you agree. Step 3. We're going to put in LTI state space form. So x dot of t. Did I show step 4? 1, 2, 3. That was step 3. Then we went back. There's 1, there's 2, there's 3. Was there a step 4? Am I having a stroke? Okay. Well, I could be having a stroke. Don't give me medical advice. That's right. That's fine. I broke it up there. That's my notation issue. Cool. Thanks for being on top of it, though. LTI state space form. X dot is equal to AX plus BU, plus all the widgets on the end, you know, the of t's. AX plus BU. X of t, U of t. Now we just need to know what the A matrix is. Well, the A matrix is partial F, partial X with all the widgets at the end at our fixed point X star and U star. We'll just write it very simply as at X star and U star. That's a little asterisk, believe it or not. Okay? So A is that 2 by 2 matrix, but we put in our fixed point. So I'm going to scroll back up to my fixed point. 0, 1. Nothing to substitute there. Nothing to substitute there, there. 0, 1, 0. When theta equals 0, you have the cosine of 0. Trig, friends, what's cosine of 0? 1, right? So it's going to be minus g over L times 1. So 0, 1, minus g over L, and 0. That's a matrix full of constants, right? Assuming gravity is not changing. If it were changing, you wouldn't have an LTI system anymore. Okay? Wouldn't be. What does LTI stand for, anybody? Linear time invariant. Whoa. What does LTI stand for? Linear time invariant, that's right. You, sir. Linear time invariant, right. Great. Now the B matrix, where we're going to evaluate partial F, partial U. And guess what? There's nothing to substitute in the B matrix. I'll scroll back up and show you. 1, 2, 3. Whoa. Right there. 0 and 1 over ml squared. Okay. Relinearized. That means you can do the analysis of this linear system. We can check the eigenvalues of that A matrix. Okay? And if you did, so some people took controls 1, they remember the concept of poles. Anyone remember? Anyone brave enough to say they remember the concept of poles? Nobody's brave enough to say they remember the concept of poles. All right. But what would happen is you would take the eigenvalues, and those are the same as poles from controls 1. Okay? And the eigenvalues of this system would be right on the imaginary axis. Anyone remember the phrase critically damped, overdamped, undamped? This would be undamped, meaning it would swing forever. Hey, like a pendulum without damping. What a surprise, math works. That model is wrong, but it's somehow useful. It tells us how that pendulum behaves at that fixed point. What about the other fixed point? How can we know? Glad you asked. Let's do the other fixed point. Where's up high? Looks like that. So I haven't drawn a picture in enough time here. Ooh. We know intuitively what's going to happen to that pendulum. You poke it, it goes down. It might come back on the other side. Well, it's not coming back the way it came, at least not right away. Okay. So in that case, our angle, theta star, I've chosen as pi, 180 degrees up. Could be minus pi, I don't care. The math will end up the same. Fixed point has it perched up on top, theta dot star, 0 rads per second. Pi rads, and we're not going to touch it with tau stars. It's going to be 0 Newton meters. Okay? Well, my friends, a lot of the work of linearizing the system, we've just done. Right here, in picking the fixed point, and 2, taking those derivatives. Those derivatives don't change, but the fixed point did. So we could go back and say, hey, our B matrix, there's no variables in there. There's no states, there's no inputs. That doesn't change. The A matrix, though, has theta of t in it, right? So we just change the theta that we plug into there. So now, instead of being cosine of 0, it's now cosine of what? Pi. Yes, pi. What's the cosine of pi? -1. So now, we fast forward, our A matrix is now going to be 0, 1, minus g over L cosine of pi, and then 0. And our B matrix is 1 and 1 over ml squared. It's all the same. Right? See, everyone's extremely excited. Now, you plug into your calculator or just remember trigonometry to know that that cosine of pi is equal to -1. Therefore, our A matrix is going to be 0, 1, positive g over L, 0, and our B matrix is I'm just writing it again for good measure. New dynamics, who dis? New linearization, who that? I don't know phrases. The only thing that changed was that. But if I go and check the eigenvalues or the poles of that matrix, it's unstable now. Okay? Any questions about that? As a form? Yes, yes, I see 2. Yeah, Christian and yeah. I'm sorry, could you repeat the question? Sorry, I didn't hear you the first time, but okay, your question's no longer relevant. Glad to hear. Thank you very much. I get so excited. I apologize. Not for the mistake, not the excitement. Okay, that should be 0. Thank you, Christian. Question. Your question is no longer relevant. I can't imagine why. Thank you. Love it. Means you're paying attention. Okay, that's 0. Did I write 0 everywhere else? Yes. Close enough. Okay. All right. Any other questions? There's a formula for linearization. Not so bad, right? So now we can do all kinds of stuff with it, right? And this will get this to, we'll do a preview now for our next in-person lecture. Because on Thursday, we're gonna have MATLAB do this work for us, okay? So far, people have been using MATLAB, we're using ODE 4.5, we're using plotting, okay? Maybe a little bit of the control systems toolbox, but not too much, right? But you all know that MATLAB can take derivatives symbolically, right? You all know this. If you don't, surprise, okay? We can have MATLAB take these derivatives for us and linearize systems for us. Pretty neat, eh? Okay, that's what we'll do on Thursday. And at which point, we will have everything that we need to move back to the optimization side of the class. I'll give you a little preview and how it starts to tie back into all this linear system stuff, right? Okay. So preview, back to optimization. We haven't talked about some of this stuff in a while. Talked about it in the opening lecture, which you can find on links on the Canvas page or the YouTube channel. You need to rewatch it. Okay. Recall that an optimization problem has 3 things that we have to define. One is our decisions. What are we deciding? 2, what is our cost function? Which says how much we care about the decision, like a smaller cost is better. It defines what is good. And 3 is the constraints. Components. You have what we call a decision vector. Call it W. You have a cost function. I will change the letter of the cost function just because we just talked about the letter F, Gesundheit. I'll call it F tilde. Tilde is only here for this lecture because we had F elsewhere. Cost function, and you have our constraints. Call them G of W, less than or equal to 0. And G can be a vector. Okay. What are some of these things we could decide about that pendulum control problem? The thing that we did that we coded in class. What were some things that we decided? Because we're in charge about the controller. Anybody? Remember the K's? The gains? We chose those, right? That's a decision that you can make about so many controllers, right? So, say for feedback control, gains are common decisions. We showed that we could swing up that pendulum with gains that I chose just because I did what we in the business like to call vibes-based tuning. Choose them based on vibes. I've just done it enough. I know what a good number is. But if you didn't, this is something an optimization could choose. Assuming you knew the other 2 things that you had, such as the cost function. Gains are common decisions. Now, the cost function what's something you might care about for your controller? Anybody just want to brainstorm with me? What are things you might care about? Speed. How fast it gets there. How fast it gets where you want to go. Right? Anything else that people might care about? How what it is? How smooth it is. I'm quite smooth, thank you. Anything else? Overshooting, you don't want it to go too far past and come back. Anything else? Do we have infinite power in this world? Energy, effort. You might care about not using too much energy and effort, right? So imagine, so it's an example for a control system. We say we care about, here's a really simple version of a lot of those things, okay? Getting to where you want to go fast, but not using too much effort, okay? So imagine we had our, I won't do pendulums. I'm done with pendulums for today. I'm swearing off pendulums for at least the next 48 hours. Let's say you have some target state, some desired state. What you want to get to. Let's take where we want to go and subtract out where we are now. What's that called in controls? The error. Okay. And we want that error to go to what number typically, friends? 0, right? So might make sense to have a higher cost when that error is far from 0. Okay? So a typical cost might be error squared. That's the easy way to say that either giant, large negative numbers or large positive numbers, both are bad. Near 0 is still good. So it's a quadratic cost. Okay? Another thing, if you have some control input U, that's your control input. Maybe large positive numbers and large negative numbers are both bad. What can we do? Let's square it and put it in the cost function. So your cost could be your U of t squared. It's also quadratic. Sorry, thank you very much. Don't know how my settings got shuffled. Thank you for the comment. Cost, U of t squared. Now that's a function that we're squaring. But the cost function has got to be a single number, right? Was it good or was it bad? This can't be this time-varying number. No, 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 no. So instead, let's look at the area under the curve of that number. If it's always at 0, there's no area under that curve, right? That's good. If it's a big number for a while, and then comes to 0, there's all that area under the curve that's bad, right? Integral with respect to time. Integral with respect to time. You have a quadratic running cost. In controls, we find quadratic running costs to be practical and mathematically convenient. Easy to take a derivative of a, for instance, of a quadratic cost. Pretty easy to do. It's also smooth. There's no cusps, no non-differentiable points. It sure is nice for a number of different reasons. Okay, we're almost out of time. So I'll spare you the rest of the math here as we get into this later. So here's the rub. If you have an LTI system and you have a quadratic cost, a quadratic running cost over time, there's a formula that will give you K. Okay? For a linear system with a quadratic cost, it'll give you a gain that regulates your system optimally. Linear, quadratic, regulator, LQR. One of the principal approaches to optimal control. Now, we will be dealing with many nonlinear systems, and many nonlinear systems that we won't even linearize and still control. We will be dealing with non-quadratic costs. Notice I didn't even talk about constraints. We will deal with them in the course. But LQR, in this case, is amazing. Did you know MATLAB has a command to compute LQR? Anyone know what it's called? LQR. It's in the control systems toolbox. All right, with that, we're done for today. Please do the homework, get on it. Might be surprisingly tricky or maybe not. We'll see. Thanks very much.